I am here to introduce Matthew Todd, who's here with the University of Sydney to talk about crowdsourcing chemistry and the Tropical Disease Initiative. So please welcome Matthew Todd.
Thanks. Hey, guys. Okay, so first I should say...
You'll either need to use this mic.
Oh, is it one of these two? Okay, I can stand here, that's fine. All right.
All right.
So first I should say thanks, Carol, for introducing me and hosting the visit. Thanks also to Chris DeBona, who also ultimately set up the visit. And yeah, I'm an organic chemist. So hopefully I'm going to do a bit of Chem 101 to make everyone familiar with what I'm talking about. But also going to be talking a little bit about open science. And the purpose of my visit today really is to preach that we need tools and applications. So one of the reasons coming to Google is that your apps are very intuitive and so on, and we need things for conducting science in the open, which we currently don't have. And one of the reasons we don't have them is because people haven't designed very intuitive user interfaces for things to be used by scientists to record their work in the lab. The other real reason for coming to Google today is because I recently bought a Nexus 1 phone, and I lost the little black sleeve that comes with it. I'm hoping to get a new one. I don't know. You haven't one. Okay. So there's going to be a little bit of chemistry and a little bit of stuff about science and how we do it and maybe how we should do it. So it's quite a wide range of things. And obviously, if you have any questions, please just stick up your hand and we'll go. Okay, so a little bit of, I think I've still got an animation here. A little bit of chemistry at the start. Okay, so I'm an organic chemist. I teach and research organic chemistry in the University of Sydney in Australia. And what does that mean? Well, we make molecules. So I have graduate students and postdocs and undergrads who make molecules. So we put atoms together in specific ways. One of the interesting things about this is that as you do chemistry for a long time and you learn a lot about organic chemistry, you learn about how to do this and you become proficient at doing this, both in your mind and also with your hands. So you become good at putting things together, putting atoms together in specific ways to make complicated molecules. And this can be done in several different ways. What we do is we buy things from commercial catalogs, and then we use chemistry in a rational way to put things together. And we make important molecules that maybe are useful for pharmaceuticals or agrochemicals or fragrances and so on. And to do that, sometimes you want to make a really complex molecule which has certain properties, and you have to know how to do that, how to put an atom here and an atom there in specific ways. And it can be quite complicated. In some ways, as is shown on the top here, the molecule you might be going for on the top left might be obviously related to the thing that you can buy. So on the right-hand side there, you've got things in the box which you can easily buy and put these things together in a kind of like a Lego manner and build up a complex molecule, which maybe has some nice property. In other ways, there may be something available from nature, like the molecule in the middle on the right, which you can easily transform into something that you might want. So you can buy that in large quantities from some natural source, and you can convert it into something that you might want to use. So these are kind of ways of using nature initially to make things which are kind of complicated. But in many cases, the molecule that you might want, for example, the thing on the bottom right here, is very, it's structurally unrelated to anything that you can buy or find. And in order to make that, you might have to think in a very lateral way about how you can buy things and combine those things to make a complicated molecule. And frequently we find this. Some molecule that has some potent biological property is not simply made by a logical combination of starting materials. And this is a very creative process. So a lot of people say that there's a lot of art in organic synthesis. To make a complex molecule, you have to have a deep appreciation for the subject and think about it a lot and perceive hidden patterns. Now, the reason why this is interesting for me was because this struck a chord as the parallels between this and a chess game have been made before. A chess game also has certain rules that you follow. And in order to get to some final point, some complicated position or some winning position, you have to follow certain paths. And the number of paths diverge from the starting point combinatorially. So the number of possible games of chess obviously is a huge number. The number of different ways of combining small molecules to get larger molecules is also colossal. So the question that came to me was, well, can we analyze how to make a big molecule with a computer? And well, the answer is obviously yes, but no one's done it. Well, people have tried, but the progress is quite slow. The contrast that struck me is that Deep Blue, obviously a computer program, beat Garry Kasparov at chess. This is a defining moment for AI, I guess, for computer power and also software development. something as complicated as chess could be mastered by a computer and beat the current reigning world champion. Well, this hasn't happened in organic chemistry so far. For some reason, people have not designed software yet. People have made inroads, certainly, but haven't designed software yet that can really take on the masters, the big professors at various universities around the world who put organic molecules together. So I wrote this article about this, appealing for maybe some progress and the application of modern computational techniques to making organic molecules. And so far, this hasn't happened. Now, the thing I'm talking about today is related to this. Why haven't we, not me, but why haven't people developed tools that help scientists to do science online and in the open? That is, I guess, the message. Why can't we do that yet? Okay, so away from chemistry for a second, I have several projects in my lab, and one of them is working in an area of neglected tropical diseases. Now, there are various diseases in the world, cancer, AIDS, big diseases, and malaria too. There are some which are neglected, which means purely that the amount of money being spent on them and the amount of time being spent on them is relatively small compared to their impact socially. And there are several examples. Here's a graph from a website that lists several. They usually have rather complicated names to say, but the one that I'm interested in is this thing called schistosomiasis, which used to be called bilharzia. It's a parasitic disease occurring primarily in the regions shown on this map, so it's mainly a sub-Saharan problem. And it's a particularly nasty disease. It's a parasitic disease, and a parasite infects you and lays eggs in you, and these are excreted into fresh water, and then these can be taken up. The parasite matures and is taken up by a snail in fresh water. And then the parasite matures again in the snail, and that excretes it into fresh water, and then you pick it up again. So it's a cycle, rather like malaria, with a mosquito as the intermediate host. But instead, now you have a snail in fresh water. And it's unpleasant for several reasons. One is that the egg burden in you, in your major internal organs, can become very bad, and you begin to get very sick. You don't necessarily die from this disease, but it affects you by morbidity, so it makes you very sick, and it means that children, for example, who get the disease can't develop properly. They tend to have stunted growth, and they're very tired, they don't go to school, and this kind of thing. So neglected tropical diseases like this often are measured by something called a DALY, a disability-adjusted life year, which doesn't take into account the number of people who die, but it tries to quantify the impact of a disease on society. And by that measure, schistosomiasis is actually a big problem. Affects more than 200 million people have the disease, and another 200 million people are at risk. Really colossal numbers, actually. Now, this disease is unpleasant, but thankfully there is a good drug for it. And as with many tropical diseases, actually, there are drugs available to treat these things. They're not tremendously good drugs necessarily, but they're inexpensive, small, easy to make. And a few people around the world have been suggesting that we really need to focus on this, that maybe the drugs aren't fantastic, but at least they're there and we can use them, and then we can distribute them for a low price. So, for example, in the case of schistosomiasis, the Gates Foundation, way back, 2002, I think, but maybe I'll be corrected on that, funded something called the Schistosomiasis Control Initiative, which operates out of Imperial College in London. The guy who heads that up is a person called Alan Fennick. Now, his idea was that we have one drug available to treat schistosomiasis, and I'll come to that in a minute. And what we really need to do is distribute this drug enormously widely to reduce the morbidity of the infected populations. So we take the drug and we just distribute it to whole populations of countries. And this is now happening in select countries in Africa, and other countries in Africa have also begun their own national control programs. So there's an article here in Public Library of Sciences, Neglected Diseases, a whole journal devoted to neglected diseases, called Africa's 32-cent Solution for HIV/AIDS. It turns out also that this drug used for schistosomiasis can also be used to try and slow the transmission of HIV/AIDS in Africa. So there's renewed interest in the drug also from the position of HIV. So in general, the idea is that we try and use things that we already have. So here is the drug that's used for schistosomiasis. Now, this is a very small molecule. For those of you who dropped out of chemistry, organic chemistry, the lines are bonds, right? So where the line changes direction, there's a carbon atom. And where there seem to be double lines, that means there's two bonds between a couple of the carbons. The oxygen's obviously the O, and the nitrogen's N. They have double and single bonds. There are rings there, but this is a small molecule. This is a very small molecule. And this drug was found through a screen. It's not a naturally occurring compound. It was found through a screen of similar compounds, initially actually for a similar disease in cattle. And I don't know the story of how it was worked out that it helps people. I don't necessarily want to know that story, but it was found out and the drug was developed. Now, this is a very small molecule and can be made cheaply. So this drug, through market force, actually, is now made by a company called Shinpung out of South Korea, who supply the Schistosomiasis Control Initiative with their supply of praziquantel, this drug. And it's got so cheap that this drug is now available for around 12 or 11 US cents per gram, which is absolutely remarkable. If you look up most starting materials you might want to buy to try and make this molecule, they will be available for more than that. So really, it has been optimized and optimized. It's off patent, obviously. The drug has been optimized and is now available for a very low price. So this is great news. Sadly, the news maybe is actually too good. When a drug is this cheap and is being distributed to this many people and killing this many parasites, you have a problem. Evolution tells us if you try and kill something, it's going to do something to try and stop being killed, right? So the parasite presumably is going to become resistant to this or develop tolerance. And this is a big issue for schistosomiasis because there are no other drugs available to treat this disease. So we're in a very dangerous situation. We're using a drug to treat literally millions of people. Sometimes whole countries and villages and cities are being treated with this drug, and there are no backups for when this drug fails. Now, there will be some people who will say that resistance will not appear, and others who say it will appear, and there's this debate going on. My take on this is better to be safe than sorry. So a lot of the research that we're doing in my lab to do with schistosomiasis is to, for example, develop new analogs of this drug before they're needed. So drugs with a slight modification. It turns out in medicinal chemistry, if you have a drug like this and suddenly it becomes ineffective through the development of resistance, you can change a little bit of it. You can introduce a little group on the left or a little group on the right, and you might be able to regain potency. So we're trying to look at thinking about simple modifications to the structure, which is because that's what we do. We make molecules. Another thing we might want to do is trying to find out how the drug works. And still, after more than 30 years of use, the mechanism of action of this compound isn't known, which is quite extraordinary. Apparently quite a common situation in parasite medicine. However, there's one thing that we can do right now, and we were in touch with the World Health Organization to try and discuss how we can keep this drug good for as long as possible. And the World Health Organization's perspective is that we need to try and use this drug maximally while it's still good. And there's a simple thing we can do to try and postpone the development of resistance. And what you do is you increase the dose of the drug, right? So you give more of the drug to try and kill off partially resistant parasites. One of my students was giving a talk about this and accidentally said that what you should do is give more of the drug to kill off the partially resistant people. Which really gave the wrong message. The point is that parasites become resistant, and you don't want that to happen. So you want to, if there are some parasites which are partially resistant, you want to try and kill those off by increasing the dose 15–20%. Unfortunately, the amount of drug you have to take is large. This is a 600 milligram pill. And the field workers who've come to conferences at which I've been tell me that compliance is a real issue. If you're trying to give literally tens of millions of people a drug, sometimes in very remote areas, if the drug is too big or tastes bad, it won't be taken. People may be naturally suspicious of artificial compounds, brightly colored pills. It also turns out that praziquantel tastes terrible. So there's another compliance issue. So you can't necessarily make the pill bigger, but you want to increase the dose. So how do you do that? Well, we as chemists, we see a way of doing this. Okay, this just a little bit more Chem 101. This is an issue in organic chemistry. Let's take a few minutes out. This is an issue in organic chemistry that I wish the public understood. It's one of the most profound and beautiful aspects of the universe, and this is not known generally by the public. A fundamental feature of organic molecules. Okay, so organic molecules they're three-dimensional, unlike some of the drawings which I put up of two-dimensional things. They're three-dimensional things. They're real things with depth and structure. And the larger the molecule is, like proteins and DNA, this structure becomes very large. But they're three-dimensional objects. It turns out that three-dimensional objects can have this property called chirality. And this is all about a mirror image. So if you imagine some object, let's take a symmetrical object like a ball. If you take a mirror image of that object, the ball that you generate in the mirror looks just like the first thing you started with. So the two mirror images are superimposable. They're the same thing, basically. Other objects, familiar objects to us, don't have this property. The mirror image is not superimposable back on itself. And actually, the majority of things you see in nature are asymmetric like this. Your hands are a good example. Your hands ostensibly look the same, But if you try and put them back on each other, you can't. They're not superimposable, which is why your right hand doesn't fit in your left hand glove, right? This is very important in nature because it turns out that the molecules in nature, almost all molecules in nature, apart from water and ions and things, have this property, that they have a certain three-dimensional orientation in space. And almost all the molecules in nature have one orientation and not the other one. So if you imagine just for a second that you're walking along the street and you meet someone you know, and you want to shake their hand, that works one way around. So if I give my right hand to someone and they use their right hand, we have a good handshake. Right? If one of them uses their left hand, then the handshake's all wrong. And this is an important thing. When two molecules like this meet, you can have different kinds of interactions. And it's very important we get it right. So all of these drugs that we now take, which are now approved by the FDA, you have to define exactly the three-dimensional arrangement of atoms in space. And it can't be a mixture of the two. This was made tragically obvious by the now very familiar thalidomide story. Thalidomide is shown, those two structures on the right of the screen. And the difference only really is in the structure is that in one case, see where that nitrogen is, and you've got the kind of hashed line. That implies that that atom is behind the rest of the molecule. And on the right-hand molecule, the nitrogen has a kind of thick wedge going to it. That implies that that half of the molecule is in front of the rest of the molecule. These two things are mirror images. They're not superimposable. And if you take one, it has a very different effect from the other. So it turns out the one acts as a sedative. It was taken for a morning sickness, I think. But one of these other molecules inhibits the formation of limbs on fetuses. And so this was tragically realized when these babies were born, deformed through this drug. And since then, it's been definitely required that we have to specify exactly what we give people when they take drugs. It turns out actually this molecule interconverts the two when it's in the body, so it's not that easy. But the principle remains the same, that one of them is very bad for you and one of them isn't. This has rather nicer implications in the case of the molecules on the bottom left here. This is limonene. And the reason I've got this picture of my wife up there holding lemons and oranges is one is the picture of her and one's her mirror image, and there's lemons and oranges in both hands. One of these molecules is responsible for the smell of lemons, and one is responsible for oranges. So they're two mirror image molecules. So if you smell one, you get lemons. If you smell the mirror image molecule, you get lemons. So it's very important that we have molecules that specify exactly the three-dimensional arrangement in space. Now, why am I telling you this? Well, partly because I think it's the most beautiful thing, one of the most beautiful things I've ever seen. That this is a very profound thing about the way the world is. And I'd love to explain this more widely, but unfortunately I've got a job. However, this is relevant to praziquantel, the drug that I'm talking about. So the structure I gave you before didn't have that little wiggly H on the top. Now that carbon in the middle there, where the H is attached, is very special. It's got 4 different things attached to it, and that means that makes this molecule chiral. It means that in one case, if you imagine the hydrogen that's on the left there with a kind of wedge in it, it's coming towards you, and then on the right side you've got the hydrogen going away from you. These two molecules are mirror images. You don't really see that because I've turned it around, but they're mirror images. The one on the left is the drug that works. And the one on the right doesn't do anything. In fact, it has mild side effects. And in fact, the one on the right that doesn't do anything is the one that tastes bad. So we just want the one on the left. That's it. How easy is that to do? Why don't we just, instead of making both and giving both to people, so it tastes bad and there's too much drug, why don't we just give the one on the left, which has the right orientation? Well, that's actually quite difficult. So these molecules are difficult to make when you have to specify exactly the orientation in 3 dimensions of where all the atoms are. And to give you a sense of that, I guess if you think about the bowl here on the bottom left, it's a symmetrical structure. It's very easy to make something like this because you can have like a spinning wheel, and it's simple to make something that's symmetrical and round, right? In the middle, plugging +1, on the border +1, disclaimer, this is a more difficult thing to make because it's not, it's still symmetric, but it's less symmetric than the bowl. Suddenly you've got to make the round part, which is quite easy, but putting the handle on, you've kind of got to do that by hand. This is a more complicated structure. When you get to asymmetric structures like this Rodin sculpture, that's actually very difficult to make, right? Because you've got to, with your hands, put things in various different places. So the less symmetric something is, the more difficult it is to make, I guess. And a lot of molecules in nature are extremely asymmetric. They have little bits here and there that you have to install kind of by hand, except, of course, the molecules are very small. So how do we do this? Well, of course, we have to design other molecules that act as our hands and install things in certain places. It's very demanding. It's an area called asymmetric synthesis in organic chemistry. And people devote their whole careers, like me, to this area. How do we make molecules in 3 dimensions? So it's very demanding. And so unfortunately, praziquantel has this feature, and if you want to make one rather than the other, it's difficult. Making both at the same time is very straightforward. easy, but making one rather than the other is difficult. So this is where we were a few years ago. We thought, well, the World Health Organization wants just the one active form of the drug. It's called an enantiomer, the active enantiomer of the drug. They don't want the inactive one. They want that because then they can reduce the pill size by half. And the pill doesn't taste bad. It's smaller, and you can increase the dose even a little bit. So it's a much more effective pill. The problem is that as soon as you try and make one enantiomer rather than the other, it becomes an expensive thing. People like me have to get involved, and we have to think about ways of doing that. How do you install that hydrogen on one face of the molecule rather than the other when a molecule is so small you can't put it there with your own hands? So we were thinking about this, and unfortunately the drug is already very cheap, so how can I justify assigning academic resources to reducing the price of something? I would be fired if I did that, right? That's not academic work to try and gradually reduce the price of something iteratively over several years. This is not a problem that is solvable by academia by any means. We are obviously in the business of trying to get out high-impact research in new frontiers, and we're not in the business of reducing the cost of anything. On the other hand, if we turn to industry, they would not be interested at all in this problem because there's no money to be made in tropical diseases. There's no money to be made in taking an already cheap drug and trying to modify it a little bit. So there's no real market value for that. This is already a very, very cheap process to make the combination of the two enantiomers. So we were left with this problem a few years ago of thinking, well, this is an important public health problem that the World Health Organization would like to solve. We can't solve it with academia, and we can't solve it with industry. And this seems like an impasse, right? What do we do? If I try to, this graph is meant to indicate that if I try to assign people to increase the EE, this is called the enantiomeric excess, which is a measure of how much of one of those molecules you have rather than the other. And you try and increase that by piling dollars on the program, it doesn't really, you get to this point where you can't anymore assign any more resources to this problem. You've got to reach a breaking point where you say, I simply can't justify this anymore. And simply as you assign more people to this problem, you think, well, is this really worth our while? How do we do this in traditional models? We can't do that. So in the case of this, we thought, well, I was actually on my honeymoon at the time, and I was thinking, how do we solve this problem? What I need to do is try and collaborate with as many people as I can. So this was new to me a few years ago. And it turns out that, of course, well, you guys know all about this. You guys know all about open source things. The idea of open source is being somehow illustrated by this comparison between the cathedral and the bazaar. So in academic research in chemistry, by and large, we operate on the cathedral model. I am the professor in charge of students, and I have my resources, my grants, and we work usually pretty much in isolation, using the supposed intelligence of me and my students to try and solve problems. We're this autonomous unit that does collaborate occasionally with select people, but we are a closed unit. And we were thinking about how to try to solve this problem, and we couldn't. The contrast between the cathedral is the bazaar, where anyone can contribute, and everyone's opinion is valid, and you listen to many people as possible, and you try and find a solution to a problem. Now, you guys will know a lot more about this than I do, so this is new to me, and I haven't read the requisite literature about this, but this was the essential contrast that we were seeing, and basically we don't operate in science on the bazaar model. We use the cathedral, so we don't tend to discuss problems openly with strangers and a large number of people we don't know, and try and get a solution through the community. It just doesn't really happen. You tend to publish papers in academic journals, and people might respond to that, but it's a very slow process. There's no direct discussion between people unless you actively collaborate. These are very different models, and as I understand it, things have gone very well for the bazaar model in open source. So from my naive non-computer science perspective, it seems as if projects like Firefox, Chrome, Wikipedia, these things have gone extremely well, extremely powerful programs that have developed really quality products. I think a lot of people tend to associate, outside the movement, people tend to associate open source with endeavors which are purely done by volunteers and which are not funded. And of course, this is wrong. From what I hear, a lot of projects that are open source have involved a funded kernel of activity to which people then respond and help out. The example that maybe that's relevant here is, as I understand it, the Chrome browser was developed by guys here, but is open source so people beyond these walls can help change, modify, and update it. That's my understanding. But how to be put right on that? So schematically, I put these together. This is two, again, rather naive ideas about how you do things in the two different ways. It's been pointed out I should have put some women rather than the men icons. Sorry, I was in a bit of a rush. So on the left here, you have the traditional way of doing science, which involves people working in labs, submitting articles to peer-reviewed journals, waiting a few months, and then the reviewers of that article, who are anonymous usually, maybe one or two people say yes or no. The article gets published, and then people read that in the literature, and then people design their own response to it, do their own research, publish an article again. The time scale is quite lengthy here. It involves months of waiting around while the review process happens. And in some cases, peer review is, of course, flawed. I don't want to get into that discussion right now, but peer review is an excellent system, but it does have these big flaws that sometimes you can get referees who maybe are not impartial. Maybe they're a vested interest. Maybe sometimes there's only like one referee on an article, and then that appears in print, and it's then sanctioned as being valid. Typically, articles published in academic literature don't have feedback on them. If you want to criticize an article, you have to publish a substantial paper that refers back to the original. It's not a very interactive process. It's also fairly slow. So the calendar icon there is meant to indicate that it's a slow process and costs a lot of money. We apply for a lot of money to do this, and in some cases we're competing with people who are doing similar research to us. So in many cases we may be duplicating effort. On the right, the idea is that instead of doing that, why don't we post a problem to the community, have as many people as we can reach helping us out with the scientific problem, and publish our results in real time, which are then peer-reviewed after they appear, so after publication. This is not a model that operates in science at the moment. So this is not how we do things at all. Science operates pretty much on the basis of peer review, before publication, not after publication. So Wikipedia is anathema to a lot of scientists because corrections happen after something is made public. Notice that, so open science is the thing on the right there, that data would then be published in real time as it's acquired, and people would be able to respond as they see fit and collaborate with you in real time, even though you may not know who these people are. This very important qualification is this is not the same thing as open access in journals. Open access is where, of course, you can read things for free, but the research may have been done in a very traditional way. Open access is a very worthwhile pursuit. Journals, it's very important that journals are open access, but it's not the same thing as open source or open science, where community participants can actually have an input into the project itself. So if, for example, I design an organic synthesis of a molecule, anyone, and I posted that as an open science project, anybody in the world could then come along and say, no, I don't need you to do that. You should try this, and in fact, I'm going to try that in my lab, and I'll get back to you with what's going to, with the results of that synthesis. So anyone can change the project and repost it for further community input. It's a very different way of doing things. Okay, so I should mention that a lot of people are doing this already. Some people, they know who they are. Up on the top left there, for example, is Jean-Claude Bradley, who's at Drexel University in this country, who has something called Useful Chem Project, the Useful Chem Project, which is, its aim is to do open science, where he's trying to make molecules that will eventually be used to treat malaria. Jean-Claude actually practices something as a proponent of something called open notebook science, the extreme form, I guess, of open science, where your lab book is on the web completely for everybody to see. So every single datum is published on the web. There's a picture there of Steve Koch, who has a biophysics lab at the University of Arizona, who also has everything he's doing is on the web, and a bunch of other people, Egon Billighardt, Cameron Nail, and Daniel Meechan, who are among several zealots of the open science movement, and they're very frequent commentators on how we should do this. So there's a very passionate community, lots of people I haven't mentioned, passionate community about this that is still incredibly small, and we tend to have meetings where we all get together and talk about this thing, and the outside world, the larger scientific effort, doesn't tend to pick up on what we're doing, unfortunately. However, there are examples on the web of lots of projects which have used open methods. This is a smorgasbord of all these things, and they vary a lot. So, for example, on the top right, the GenBank initiative, that's not really open science. It's a depository of information where people can deposit genetic information and can be retrieved free. This isn't really open science because you're not really changing things and collaborating on the site, but it's open data, a very important, massive open data resource. The Foldit program is an interesting one if you haven't seen it. It's a game which the public can play to try and help people to work out how proteins fold. So in a very ingenious bit of software development, somebody made a computer program to allow the public to get involved with that. And it turns out the public are very intuitive about this and have really good ideas about how proteins should fold, amazingly. The Open Dinosaur Project is something where the public are being involved in measuring bones of dinosaurs from the literature and collating data. Galaxy Zoo is something similar in astrophysics, where people are classifying galaxies. These are projects where public input is required and used very effectively. On the other hand, there's something called the Tropical Disease Initiative, which was started by several people, including a guy who gave a talk here called Marty Renom, which is a sister site to the site that I'm involved with. There's also a big movement for trying to find drugs, for example, for TB, called the Open Source Drug Discovery Project, which is an Indian project, which was started fairly recently. And then on the bottom left here, you have something called ChemSpider, which is a community-centered resource for chemistry, very unusual. Chemistry has an unusual history. We have a lot of very powerful, very wealthy organizations who have become involved in collating and curating chemical data. And these things are usually, these applications are usually quite expensive, and universities tend to buy subscriptions to these things to gain access to information. If you're not at a university which has that kind of resource, has those resources, then it can be quite difficult to get your hands on that kind of information. But ChemSpider is something which is on the web, and anyone can upload chemical data to ChemSpider, so it becomes a community-centered resource, and was recently purchased by the Royal Society of Chemistry, who is keen to promote this. So this is a selection of different things where open projects are involved, or open data are involved, and some of them, like the Galaxy Zoo and Open Dinosaur Project, are actually where there's community input, so public input to the project. Open Wetware, the last thing I want to mention, is a site where anyone can have a lab book online, free, and post data of any kind that they wish. It's a very impressive initiative, operates on the basis of a wiki. So in order to have a page on this, you do have to be a little bit savvy with how to write wiki pages. But it is completely free and open, and anyone can have a lab and a lab book on this site, so it's very impressive. We started out a few years ago with this website called the Synaptic Leap. So if you would like to see more about it, please just Google us and have a look at it. The idea is it's a basic blog functionality. And we posted our problems with schistosomiasis on this website. The intention of the site is actually to be an open science site for anyone to conduct any projects they want in anything to do with biomedical research. We started with the schistosomiasis project because there's a philanthropic angle, I guess. The idea of spending some of your spare time helping us out when this project is to do with a neglected tropical disease gives participants, good karma, right? So people feel good about contributing to this. But really, the aim of it is to have something which is wider, so you can do any kind of collaborative biomedical research on the site. So up on the top there, there's the Schisto research community, and on the bottom there's an example of something that my postdoc recently did, which is a chemical reaction, which we did in the lab, and beneath that diagram there's all the data about how that worked and what happened, including the raw spectral data of what we did. Now, I just want to mention something about this. This is a limited functionality. It still operates as a blog. It's built on Drupal. And I don't know about you, but whenever I see a blog post which is interesting and for which there are several comments, maybe 10 or so comments, by the time the comments get to about 10 or so, I tune out. I can't be bothered reading them. A blog functionality is really quite limiting. You can't do a huge amount with this. And in terms of community input, it's actually quite limited in what people can do. What we really want is to have this, but much more intuitive and functional. At the moment, it's very linear and very flat. We're doing our best with this, but I think we need something that's much more intuitive. And that's really what I'm trying to get at here. Just before I get on to the nitty-gritty of that, just a couple of other advantages of open science more generally, the idea of doing this on the web. So the project we're posting here, of course, is asking the community to help us devise a synthesis for this molecule for a very, very low price. The other advantages of doing science like this on the left is transparency. You may have heard about the controversy surrounding the climate change emails in the UK, the University of East Anglia. This idea that the public thought that there was science that was being hidden from public view, where perhaps some research allegedly was being suppressed because it didn't agree with the idea of climate change. This doesn't do science any good to have this kind of public perception of what we're doing. And there's a real advantage in doing open science is that everything is transparent and you can see what's going on and nothing is hidden. And I think in terms of a public engagement with science, that's going to be very important. In the middle is this picture of a starfish. Again, this is apparently an IT analogy, the starfish and the spider. Open projects don't have leaders. I mean, I'm the leader of the project that we're doing at the moment, but I don't have to be. The project is the important thing. And if I decide to do something else, or if I am called away to do something else, then somebody else will take over. It's a leaderless organization, which is a big advantage for open projects. Somebody can take over. Anybody can take over, and anyone can take on side projects and lead things. The third picture is meant to imply speed. To me, one of the big advantages of open science is speed of progress. My theory is the thing that we're trying to test out in the next few years is an open science project where anybody can contribute and experts identify themselves will operate faster than a closed lab project. That's the hypothesis. And we are hoping to try and test that in the near future. But we're starting with our synaptic leap project for this drug. The picture of the plankton here is meant to remind me that the one important lesson we've learned with open science over the brief period that we've been doing it is something which I think is very well known to IT professionals who have been working in open source, which is that it's not enough to post a problem and have the community input. You have to post data first. You have to post results, a kernel of activity to which people respond. And this was very clear to us with the Synaptic Leap, which for the first couple of years of its existence was very quiet because we had no funds and no resources to put people on the project. We then went the long route and asked the Australian government for funding for this project with the World Health Organization as our sponsoring partner. And we secured a grant for this project in mid-2008, which took a while to get signed off, but is now active. Now we have somebody working in the lab who's posting real research data as it's going on. And that means that people have a lot more to get their teeth stuck into. We've just started, but it means that people can now respond to us. It's crucial, I think, in any open science endeavor or any open source endeavor to have sometimes a funded kernel of activity which people can respond to. That's our important lesson. Okay, so I want to say something about experimental science, and then I want to do my appeal for applications. So this is the real nitty-gritty. Being an experimental chemist, being an organic chemist, is very like being a chef. You have things at your resources. You buy things in. You combine them with various apparatus, which you have in the lab. A lot of things in the chemistry lab have a corollary that's in the kitchen. It's amazing. You have, a gas flame in a kitchen. We have a Bunsen burner. You tend to boil things off. Maybe you want to reduce something and take water off something. We have something for that in the lab. Lots of things that we use in the lab are very similar to kitchen kind of chemistry. This is a picture of one of my students, Hamid Munir, who his bench is right to the left there, and he has all the stuff laid out. And his fume cupboard, which is the thing he uses for toxic stuff, is behind him. A bench chemist will come in early in the morning, 8 o'clock in the morning, will think about what they're going to do. They'll design an experiment. They'll get their chemicals together and use glassware and metal things and a bunch of different things to do their chemistry. They'll run a reaction. They'll effectively taste it, as you do when you're a chef, by sticking a spoon in and licking it. In the chemistry lab, you never do that. But there are ways of testing what's happening in your reaction. And then you isolate the thing that you've tried to make. You analyze it with some instruments, and then you write up what you've done. This is what a chemist does in their life. The analysis is kind of complicated. As a chef, you taste things because your tongue is a very sophisticated thing. In the lab, you have to take the molecule that you think you've made and put it into some very large, expensive instrument, which then analyzes if that's the right thing. There's a lot of data here. For example, the instrument we use the most, we take our molecules and we put it into this large superconducting magnet. And we spin this molecule very, very quickly, and we blast it with electromagnetic radiation. And rather like when you hit a bell, you listen to what comes off the molecule after you've done that. So when you strike a bell, you're going to listen to the tone. And of course, what you get off the bell is all this sort of vibrational data, which is very complicated, and your ear transforms that into one note. Similarly, with something called NMR spectroscopy in the lab, we take molecules and we blast it with this radiation. We get this very complicated signature that comes off. We do something called a Fourier transform and get these lines on a piece of paper. And the signature on those lines and how they appear allows me to say, yes, that's the molecule we thought it was, or no, it isn't. Lots of big instruments generating lots of data. But in a typical day, a student will use all of these different things. If that student is meant to tell another student how they did something, how do they do that? Well, they can write up something in a traditional paper. That often hides little things that you might have done which are special. In the same way that a recipe book, often recipes don't work. You don't quite follow the instructions right, or something was just missed out, or there's a decimal point wrong somewhere. If you want to capture the research process, you need ways of doing that are really quite data rich. So you want to be able to capture things with audio and video. You'd like to be able to post raw data to a website rather than the interpreted lines that we tend to get. So maximize the amount of data that you publish. And really you want something which is quite intuitive and rich if you want somebody to follow what you've done. For example, also in the lab, that's me talking to one of my students, Althea. We have these fume covers with kind of Perspex covers, and often we write on them like you write on whiteboards at the back here. If you're going to collaborate with someone, you want to be able to easily collaborate with them as if you were sitting next to them with a coffee talking about science. And really, at the moment, we can't do that outside my lab. We can't collaborate with people who are outside of Sydney, outside my lab. If we've got a problem, we go down the corridor and talk to a colleague. But if we want to throw this project open to the world, we need a really intuitive way of collaborating as we would in a normal lab. How do we do that? And how do we maximize the input that people are going to give us? Well, something which I think maybe some of you will know as IT professionals is something called Stack Overflow. Maybe some of you have heard of that, which is a site where you can post code and ask people to help you out solving certain problems. With code, that works really well because you can cut and paste code and stick it on the web page, and people can rapidly respond. It's also a very nice idea because you can have medals awarded to you for valor of service, right? And your reputation increases. So it's a good way of trying to develop a reputation for yourself as someone who can help people solve problems. Of course, that's good for text, but for experimental science, this just doesn't really exist. Something has been started, Campedia Lab, by a guy in San Diego, Rich Apodaca, who has taken the basic functionality and tried to use it for chemistry. At the moment, it's quite text-heavy, but it's a very good idea to try and use the same idea in experimental science. Of course, what we need is something, again, that's still very much more intuitive and allows data-rich things to be posted, allows links to online pages where all your data are posted, allows links to online lab books for science. So basically, the structure we need is something which is an intuitive lab book online, where all the data are linked with your experiment, and which can easily be analyzed by somebody else as part of a collaboration, and collaborators can post to your web page. Type text. And that's fine, and you can post something like that. But there is no chemical content in this. They're words, and they are not understood by a machine to be referring to molecules or chemicals. So the text is quite dead. And if anything was going to search this, you wouldn't really have a lot of input from the computer about what is chemical information and what isn't. To be able to take text and convert that to something which is chemically rich, so where a word is associated with a molecule and can be searched and analyzed and indexed, would be tremendous for HTML, XML. And a guy called Peter Murray Russ developed a language called CML, which is chemically rich markup language, and has worked with Microsoft, I don't know if that's a rude word here, worked with Microsoft to develop a chem word add-in, where a Word document can be searched by a machine, and the chemical information can be annotated and extracted automatically. So when you hover over a word, you get a structure, and you can change the structure, and that changes the word. So in a PhD thesis, for example, this becomes a very rich document, where all the chemicals are part of the actual fabric of the text, and are not simply words. Another example that's just recently brought to my attention was something called chemicalize.org. This takes any given web page and extracts chemical information. And you can see what's happened here is that in the usual Latin text you get on pages, it's spotted beta-carotene, which is a molecule, And if you hover your mouse over that, you get the structure of the molecule. If you click on that, you get taken to a page where there's a bunch of chemical information about the molecule. This is very useful and makes, for example, HTML pages very rich for a chemist. It means they can be searched very effectively. We could do with something like this, actually, for Drupal. So given that Drupal is open source, what we really need is an extra button on this menu up here, which says, OK, take the text that I've just entered here, scan it for chemical information, and please annotate these individual words so that the page, when it's published, it's clear that these molecules are in there. So if I write the word benzene and I click this little button, it spots, oh, yeah, that's a molecule. And then on the HTML page it's published, that becomes an active word that can then be searched effectively and can be annotated in this way. That would be a very nice project that we could do, which would enhance Drupal a great deal for chemists and make the resulting web pages that we make much more functional. Okay, so the last, just summary of where we are. This is my son Harvey's playing with his first molecule, which is great. Start him early, you know. But this is how I feel with open science. I have absolutely no idea where we are going to be definitely going and how we're going to get there. But it feels right. It feels as though science that is thrown open, where anybody can help us out and nothing is kept secret, is the real spirit of science. It's fast, and it's transparent, and it's generous of spirit. This project that we're doing, where we are trying to get the price down of this drug with the World Health Organization, we've got another 2 3/4 years to solve that problem. It needs to work. We have to be able to show that by massively distributing a collaboration like this, where everything is in the open, we need to show that we can do that. And we need input from chemists all around the world, particularly process chemists who work in industry, to help us with this problem. The price constraint is extremely severe, and it's a real challenge for an organic chemist. Of course, what we'd like to do eventually with open science is to move beyond philanthropy. We are doing a project which is organic chemistry, so it's hardcore physical science, but it does have a philanthropic element where people might contribute because they feel good. What would be nice is to try and move into an area which is academically hot, where there's a lot of activity at the moment, and people are competing with each other to show that an open science project can actually generate papers and results faster than traditional closed collaborations. That would be quite exciting, but it's not something that we're doing right now. Generally, the dollar sign there indicates that, contrary to what may be thought by many people about open source, open science also may well need funded kernels of activity, where small projects are funded, and lots of the scientific community can respond to us. Now, that to me would be extremely attractive if I was a funding agency who wanted to fund scientific projects. If I was a government agency and I wanted to fund scientific projects, what I would do is try and fund a kernel of an activity and then have a wider group of people help me out, so leverage more activity from my funding dollars. There's an advantage there, of course, that I've covered before, is that once the funding runs out, the project doesn't have to stop. It's this leaderless organization. The project can continue. And I guess the last thing is a more general point that open data are very important. The idea that open science, of course, shares data with as many people as possible. And this is always going to be a good thing, that if we have data in labs, which the public have funded through taxes, those data should be available for anybody to see. And open science obviously necessitates open data. That's part of its reason for being. My main appeal, of course, though, is just to close, is that at the moment we do not have really good intuitive tools for scientists to collaborate over large distances effectively. We have tools that require tutorials to use. My students are very busy. They're very busy making molecules in the lab. And I know what's going to happen if I ask them to try and learn how to write a wiki page or sit through a tutorial about how to use something. They are going to say they're just too busy. Those are my students, some of the most receptive to this that I know of. Trying to ask an experimental science student to learn something before they can post their data online, to me is like asking Gordon Ramsay to learn Arabic, right? That's just silly. He wants to do his cooking and generate a product. He doesn't want to have to learn a language to be able to do that. And with chemists, with experimental science students, we need applications which do not have tutorials in them, so that scientists can rapidly get in and comment on each other's work and share data effectively. So given that I've never needed to look at a tutorial for a Google app, I came here, right? So I use Gmail and Google Docs and Picasa without reading anything. I just started using it because it was intuitive. If we could develop that for a lab book, for an open, shared electronic lab book, that would be fantastic. My lab is collaborating with a guy called Jeremy Frey at the University of Southampton to try and link online electronic lab books to machines in a chemistry school, so data are meshed with an experimental technique. If we could expand this to have a front end that was incredibly intuitive to use, I think we'd go places. And I think a lot of scientists would love to share what they're doing if they had an effective, intuitive tool to do that. And that's really my appeal, is for something like that to happen. A dialogue between IT guys and experimental guys, PhD students in the lab who know what they need to try and develop a real killer app for an online shared electronic notebook. Okay, so with that, I won't take any more of your time. I just want to thank Carol again and Chris, and thank you guys for coming along and listening to this idea. Thanks.
Scientists still need to get tenure and fame and all that kind of stuff. And how does that work when inventions are spread out?
Yeah. Okay, so the idea that if you open everything up to the world, you're going to commit professional suicide. Yeah. I mean, that's at the moment. I think that's certainly the perception. There are some brave souls who are doing it anyway. A couple of people I just mentioned. It's interesting. There's this prejudice that if you publish data online, you can't then put it into an academic journal. And actually, for some of the high-impact chemistry journals, that's true. So I can't publish in certain big journals if I've already released data. In many cases, that's not true. So if I have published everything on the web and I decide to summarize that in a paper and I submit it to Nature, they'll take that paper. So there are lots of journals which are happy to do that. But this is a test case. How many journals will take those kinds of papers, and how effective are they? I think that if you can do that, if you can still publish your work in journals, which are traditional journals, then I think you'll be okay. The question about whether you get scooped is another thing. So if you have a great idea and you then put it on the web, what are you going to do? Of course, if something is commercially sensitive and you want to patent it, then of course you can't do that. That's off limits. But if something is not, and it's something which you don't foresee to have commercial interests, my theory is that by opening it up, by recruiting more collaborators, your science will actually go faster. That's my theory. But no one's done that yet, and I don't know if it's going to work. There was a nice example last year, I think, a guy called Sean Cutler, who's a biologist at UC Riverside, I think, who had a nice result that he found. He's a plant biologist. Had a nice result that he found. And rather than publishing his nice result, he went out actively to recruit his competitors. And then together they published a much larger piece of work in the journal Science, which is an incredibly high-impact paper and amazingly well-cited. The idea is that you can go out and actively get people to help you out is anathema to a lot of scientists who maybe don't necessarily want to trust their competitors with what they've done. But I think this is the next exciting frontier to me, is whether it accelerates your science. If it does, then I think tenure committees would be rather excited about it. All right, thanks. Thanks, guys.